Welcome everybody to our tutorial about Apache Giraph. It's an open source software designed to deal with large-scale graph. We are six students from La Sapienza University in Rome, and we did this tutorial for the data mining course. Okay, our plan is to start from the very basic concept and then get our hands dirty with some simple coding in the Giraph paradigm. Okay, so let's start. First of all, what's a graph? A graph is an abstract representation of a system in which objects are defined either as vertices or as edges, where edges are any kind of relationship that intercurre between a pair of vertices. A computer network is a very simple example. As we can see in the bottom right image, we can define as vertices every device that are connected through a local network. A roadmap is another possible example in which vertices are just cities and the edges are the roadways between them. Web obviously is a huge graph in which every page can be seen as a vertex, and links can be represented as edges, and the relationship intercourse between them in a unidirected way. Social networks is another example of a graph in which users are simply the vertices, and each relationships between them can be represented as an edge. Okay, now what are the main problems for which we need something specific to deal with this graph processing? Well, first of all is the dimension. As we can see here, the main studied graphs have a very high dimension. First of all, Google, but also Facebook, Google Plus, and Twitter are huge. And to process some algorithm in this huge data set, another problem arises when we find out that each vertex depends recursively on its neighbors, and so algorithms in them must be applied in an iterative way, and so this is why we cannot use the main commonly used paradigm to deal with big data. That's MapReduce. Okay, we can see here a brief schema about how MapReduce works, and we can see that the main use of this paradigm is to split the job between a cluster of computers by a mapping function and a reduce function that compute the partial results on the data that are mapped to them. But the problem in here, as we can see, is the intermediate files stored on disk, and this makes arise quickly in an input-output domination in time in the algorithm. Okay, this is why Google firstly came out with the idea of Google Pregel, that is a software specifically designed to deal with these problems and to large-scale graphs processing. The main idea that is developed here is the user interface that makes you think like a vertex, and this is developed with the bulk synchronous parallel model that my colleague later will explain you. And they and also it has a fault tolerance by checkpointing.
So let's talk about Giraph. Giraph is a software used for implement iterative algorithm based on graphs. It's used on many applications like the Facebook graph. It's used also to analyze data that belong to Twitter and Yahoo. And Giraph, born as Google Praggle open source counterpart in 2010, then become a top-level project of Apache in 2012. Now we have the version 1.1 that it has been released in 2014. How does Giraph works? Well, we are in a distributed systems and implementing algorithms for Giraph means implementing a function that is executed by each single nodes. A nodes have limited knowledge. A node simply knows only his ID, a value, the list of neighbors, and corresponding edges values. Implementing an algorithm for Giraph means implementing algorithms that are executed by the single vertex. So this means you should think like a vertex. Then each vertex compute a partial solution in each iteration because Giraph works in iterations. And when it has computed its partial solution, it spread the solution among the whole network. Giraph use the bulk synchronous parallel model. What does it mean? It's a model that rules distributed system by splitting the dataset in various partitions that assign each partition to a worker that can be a single machine or many workers can be hosted on a machine. It's a master-slave architecture and simply works in this way. Each worker computes the partial solution based on the partition of dataset that he keeps. Then once the partial solution is reached, it spreads the solution to the network. Then it waits to the synchronizing barrier. How does Giraph use this model? Well, at first time, the dataset is splitted. What does it mean, splitted the dataset? Well, we are talking about graph. So splitting the dataset, it means to assign nodes to workers. So each workers keep a set of nodes. Then each worker can compute a partial solution. This means to run the algorithm for each node. When a workers have computed the solution for each node that it keeps, it will send messages to the whole other workers. Then it waits to the synchronizing barrier. When all the workers have reached all the messages and no workers still need to send messages, it can start the next superstep. Starting the next superstep means first reading the message received in the previous superstep, then update the variables in a dependent way from the message received, and then start to compute the new partial solution. What are the advantages of this model? Well, at the start of any superstep, each worker read the messages received in the previous phase. Then it has all the variables that he needs for ending this step. So the situation that a node is waiting for some variables from other nodes cannot happen because when a superstep starts, all workers have all the variables that it needs. It's a global synchronization because it simply starts any supersteps when all the workers have done their tasks. And this model is massively parallelizable because adding another worker just means to assign some nodes to these workers, and then all the workers will achieve the partial solution independently from all the other workers. The architecture of Giraph is based on the Hadoop distributed file system, and then it's a master-slave architecture. We have in the architecture a master that is just node the network topology, and it can run some module like the coordinator, the zookeeper, and the net. The coordinator just rules the network. The zookeeper can provide some module like combiners or aggregators, and each workers have a set of messages assigned by the master in the first phase, and then for each superstep we compute a partial solution that is spread in the network by the netty module. We can see from this picture that we have a set of nodes for each worker and two boxes of messages. The inbox messages keep the message received in the previous phase, and when the superstep starts, it reads the new values of the node inside the inbox message. Instead, the output box just keep the partial solution computed, and once all the vertex have executed the algorithm, the message will be spread by the netty modules. The job schema of Giraph is very simple. First of all, the vertices are routed into Giraph. What does it mean? That the master simply split the graph and assign a set of nodes to each worker. When all data has been loaded, the computing phase will start. What does it mean? That each worker calls the compute function, and for each node of the set that the workers have, it computes a partial solution. When it has computed the solution for all the nodes, it's simply send all messages, and then wait the synchronizing barrier. When a worker have stopped sending message in this phase, another phase can start. Sooner or later, depending on the algorithm behavior, all the node will reach a solution. Then no new messages will be produced. So this means that the workers together have reached a solution. So in this case, we can start the floating phase and produce the output. Some other hints that can be useful and very powerful in Giraph are, for example, the aggregators. That aggregators are commonly used by the master workers, but can be also done by single workers, and it keeps the global values. As I said, no workers is aware of the whole graph, so keeping a global value is it's impossible for a single worker. So this is the reason why exists aggregators. Some function of the aggregator, like sum, max, and minimum, are predefined, but it's easy to define other function. Of course, each global value is calculated in the successive step. So at step t+1, we have the value of the step. Another useful feature is the combiner. Typically, it runs also on the master, and it's useful for decrease the network I/O. What does it mean? Giraph produces many messages, many short messages, because typically it's a single value, but each worker can keep a set of big nodes. So it will receive many messages for each node. So it's not very efficient. So combiners will group all the messages directed to a single worker, and in this way will decrease the usage of network, will decrease the metadata on the network, and increase the performances. Another feature is the checkpoint. We know that we are in a distributed system and we are talking about big data sets. So storing for each step the state of the system is not possible, but at sometimes it's easy to define some checkpoint to make the system resistant to failure. Also, the checkpointing is done often by the master, but some worker can done properly.
Hi everybody, my name is Adrian, and after this theoretical part just done by my colleagues, we are going to see a first concrete example of Giraph. In particular, we are going to compute the out degree of a given graph. Since we are talking about the out degree, this means that the graph must be directed. Therefore, first thing to do is to define the input format to Giraph, of the graph, of course. As you can see, we are going to use the long null text input format, meaning that we have a txt file where each line represents the ID of the node and the list of its neighbors, separated by a space. Now we have to define also the output format of the exercise, and we will have, again, for each line, the ID of the node and the value of the out degree of that specific node, separated by a tab. Now we can move to the virtual machine, and here, as you can see, we have a folder, a Giraph demo develop folder, inside of which there are 3 folders. The one that we are going to use right now is the out degree folder. So if we are going inside of it, you can see that there are 2 files. One that is the in.txt file that contains the graph that we are going to give an input as input to Giraph. And as you can see, we have 5 vertices, and each vertex has the list of its neighbors. So for example, node 0 has a directed edges to vertex 1, a directed edge to vertex 2, and a directed edge to vertex 3, and so on. We can close this file, and as you can see, we have also a Java file. We have to open it with Genie. Let's zoom a little bit, and as you can see, we have that our Java class extends a basic computation class, which is an abstract class, and parametric class. In particular, we have 4 parameters: 2 long writables that represents respectively the ID of the node and the value of the node. Then we have a null writable, which represents the weight of the edge between the vertex and another vertex. But in this case, we don't need the weight of the vertex for our purposes, therefore it is null. And then finally, we have the double writable, which is the format of the messages. Now, as you can see, we have to override the compute method that is a method that each vertex calls. So as my colleagues told you, we have to reason as if we are a vertex. Therefore, each vertex has 3 parameters: the value, the ID of the vertex, the value of the vertex, and the value of the age, the weight of the age, and an iterable of messages. Okay, so this compute method takes these 2 parameters: a vertex object with 3 parameters and an iterable object of messages. Now we have to compute the outer degree of this graph from the point of view of each single vertex. Since we are a vertex, we have access to our list of neighbors, because since we have to send messages to our neighbors, we have to have access to the list of neighbors. Therefore, computing the outer degree is quite simple. We just need a long writable, because the value of the node is a long writable type. Therefore, long writable, and we are going to call it vertex value equal to new long writable. Okay, now what we have to do is just to set to this variable the cardinality of the list of neighbors, and we are going to do that by typing vertex value dot set vertex dot get number of ages, which is a method that obviously returns the cardinality of the list of neighbors. We don't have to do other super steps, and therefore from the point of view of this vertex, the computation is done. Therefore, we can vote to alt. Vertex.vote to alt, meaning that the vertex moves from the active state to the inactive state. Okay, our Java class is complete. We save the file and we can close it. Now, inside this folder, we have to open a terminal. By pushing F4, a shell will open. Okay, let's get bigger a little bit. Okay, now we have to start our Hadoop environment. Therefore, start all.sh. Okay, processes needed are created, and you can check the environment by typing jps command. And as you can see, we have 6 processes that are needed in order to compute our task. Now, since we have a Java class, we need to compile it, and in order to compile it, we need the path of Giraph. Therefore, giraph.path, giraph minus path. Okay, as you can see, it's quite long. We have to copy it. Okay, copy it. And now we can compile our Java class. Java C minus class path. Here passed the path. Okay, and the name of the Java file. Okay, the Java file has been compiled successfully. Now we have to create a jar archive. Therefore, jar create file outdegree.jar, and we have to put inside this archive or the class or the java.class files. Okay, the archive has been created. Now we have to tell to Hadoop file system which is the graph that we want to compute the out degree of. Therefore, Hadoop file system minus put the name of the file and the directory inside the Hadoop file system. Okay. Now, what we can check that the file has been loaded with the following command. So as you can see, we have our in.txt file loaded. Now we can make run the giraffe workers, and we do that by typing giraph minus the name of the archive, outdegree.jar, the name of the Java class, and now we have to specify to giraph which is the input format, the one that I told you at the beginning. Therefore, vertex input format org.apache.giraph.io.formats dot long null text input format. We have to specify also the input path of our in.txt file, which is, as we know, minus vertex input path in.txt file. And we have to do the same thing to the vertex output format and the output format of the results. Therefore, minus vertex output format org.apache.giraph.io.formats.id with value text output format and the output path out. Finally, we have to specify the number of workers that we want to use in order to compute this task. We are going to use just one worker and press enter. Now we have to wait a few moments. As you can see here, it's saying us that he is waiting for 2 mappers. I told you that we are going to use one worker, okay, but there is another worker that is a master worker. So if we write here 2, then we are going to have 3 here, because there is the master mapper or worker. Okay, the computation is over. We can check what is now inside the Hadoop file system. Okay, as you can see, the out directory has been created. Let's see what is inside this directory. Okay, we have 3 files. A success file that tells us that everything went right, a log file, and the final one, a file where the results have been put in. And let's see what is inside this file. Hadoop file system -cat and the path of the file part -m000. Okay, so as you can see, the out degree of our graph has been computed. In fact, for the vertex 0, we have out degree 0. For vertex 2, meaning that for the vertex with ID 2, the out degree is 2, and so on. Okay, now I'm leaving the word to my colleague Simon, which is going to show you how to compute the in degree of a given graph, in particular of the same graph.
Thank you, Adrian. Hi, everybody. My name is Simone, and I'm going to show you how to write a Giraph job which is able to compute the in degree of a given graph. So, let's start to work. Please open the in degree directory and the source directory. And finally, open the in degree Java file with the Genie editor. As you can see, the code contains already the libraries and the signatures of the methods that we are going to use. We will write code within the compute method, which represents the logic executed by each vertex of the graph, as previously explained by Adrian. The basic idea of the function is to send messages to every neighbor at the first iteration of the algorithm, and to count the number of messages received at the second iteration of the algorithm. This procedure is needed because in Giraph each vertex contains information only on the outgoing edges, not on the ingoing edges. Hence, we need to receive messages from the neighbor in order to count the ingoing edges for the current vertex. So, let's start to write the code. The first thing to do is to check if this is the first execution of the logic. So we write this line. After that, we have to iterate for the outgoing edges in order to send messages to every neighbor of the current vertex. So we write these lines. We iterate for the edges of this specific node, and then we send messages to all neighbors. We use getTargetVertexID, that is a method of the Giraph class edge, which returns the ID of the target vertex for the current edge. The second parameter of the sendMessage function is a double number 1, but for our purposes such value is not really necessary. We could insert any value as second parameter because we need only to count the messages received, and we are interested to the content of these messages. Now we can close the parentheses and open the else branch, which represents all the executions of the logic after the first one. Here we have to count the messages received, so we initialize the variable in which store such number, and after that we iterate for the messages received in order to count them. Finally, we obtain the value contained by the current vertex through this line. We set this value as the sum value, the value describing the edges counted before. A little mistake, I will correct. And we set the value of the current vertex as the vertex value variable. Now the last operation to do is to call the vote2alt function. This because at the beginning of the computation every vertex is in the active state, and it can switch to the inactive state by voting to alt. A vertex votes to alt because it decides that from its local perspective its work is done, and the computation may conclude. A vertex that is in the inactive state is not executed during a superstep unless it has received the message. The delivery of a message switches a vertex back from the inactive to the active state. A Giraph computation is over when all the vertices have voted to alt, and no message needs to be delivered. In our case, the job is executed only 2 times, This because all vertices send messages at the first execution and count the messages received at the second execution, and at this point the operations are over. Now we can save and close the editor in order to open the terminal to compile the function just written. Adrian previously explained how to compile and run the code using terminal commands. Instead, I'm going to show you a shortcut to do these operations. Please open the Makefile. As you can see, this Makefile contains the terminal commands previously executed by Adrian, but through this file we can code them by the terminal using shorter and faster commands. Now we can come back to the terminal. The first command to execute is clean, which allows us to remove the files created by Adrian executing his code. After that, we can compile our code. So we execute a command compile. Then we execute a command copy in order to allow Giraph to load a copy of the input graph contained in the input.txt file. Finally, we execute the run command in order to execute our code. We wait. The run procedure is very slow. Okay, so we can go to analyze the output. We open the output file. Okay, the output is right. So my part is over. Thank you for the listening. I leave the word to Manuel.
Thank you, Simone. I'm Manuel, and now we will get our hands dirty and try to solve a real problem using Apache Giraph. We will see how to compute the page rank. First of all, we define ranking as the order in which search results are presented in a search engine. Before Google, ranking was correlated to the frequency of the words in the document. Think, for example, as the TF-IDF method we have seen during lectures. So, pages where the keywords appear more frequently than they do on another page are considered more relevant. In 1998, Larry Page, one of the co-founders of Google, had this intuition for computing the ranking. If a page is important on the web, there should be many links pointing to that page. More links means more probability of clicking such links and more probability of ending up on a certain page. Moreover, it should be safe to assume that important pages often contain links to other important pages. This increases the likelihood of clicking a link to an important page. It is a way more sophisticated method than TF-IDF. The results were very impressive, and we all know how the story continued and contributed to the success of Google. So, according to Larry, the popularity of a page depends on the number of linkings pointing to it and how popular those pages are. It is a kind of meritocratic method because a page is popular because it provides good content. Moreover, this method is representative of the graph structure. In fact, in order to compute the page rank, the entire structure of the graph is taken into account to define the ranking of the vertices. Here we can see a simple formula to compute the page rank. The page rank is computed as the sum of the ranking of the incoming page's weight over the total degree of a page. Then we have a damping factor that define how much important of the source page is transferred into the destination page. One thing we notice is that the definition is recursive. The page rank of each page depends on the page rank of incoming neighbors. So, how can we compute the page rank values? We need a starting point. Well, we can assign an initial value to each page and then, iteratively, compute the new page rank value for each page with the formula. And since it is recursive, when the computation will finish, ideally, the algorithm will complete a convergence. But since convergence is reached only asymptotically, PageRank is usually computed for a fixed number of iterations. In the original paper, was fixed as 30 iterations. Because from a certain point on, the values changes only slightly between the previous and the next value, so we can stop the computation. In addition, we can notice that each vertex computes its PageRank. Thus, the computation is independent for each vertex. For this reason, this algorithm is going to scale very well. Now, let's see a very quick example. As a certain condition, we put 1 on each vertex. Then, the value of each vertex is equally split over the outgoing edges. In some cases, we have 0.5 and 0.5. In some cases, we have all 1 because 1 outgoing edges. At this point, for each vertex, we simply apply the formula seen in the previous slide. Here, we are using 0.85 as a damping factor, because it's the suggested value by page on the original paper. Then we compute the result of this operation, and this is the rank of each vertex. We have completed the first iteration. Then we are ready for another iteration. In order to implement in practice this example, we need another input format for Apache Giraph, because now we have also to take care of the weight of each edge. So we can use the JSON long double float long double text input format that is going to represent an input graph as a JSON array. In particular, in this format, for each vertex we have an ID, a value, and in order to represent the outgoing edges, there is an array of destination vertices. Each destination vertices has the respective weight of the edge. It is important to remember that Apache Giraph can work only with directed graph. So, if the problem we are going to solve uses undirected graph, we have to add both forward and backward edges in order to simulate them. Now, my colleague Lorenzo will show you how to implement PageRank in practice.
Okay, let's go back 1 second to the PageRank formula. The main problem that we have to deal with is in Giraph we don't know easily the out degree of the adjacent nodes. So when for each node we compute the PageRank formula, each vertex will send the PageRank divided by its out degree, instead just its PageRank. Let's go to the code. Okay. The PageRank algorithm for Giraph is divided in two main parts. In the first part, we receive the messages from the other nodes containing the PageRank of the nodes themselves, divided by their out degree. In the second part, we will update our PageRank and we will send it to the other nodes. So we first define a variable out of the compute method that is max supersteps. It is the number of supersteps that we will run. Then we define a second variable that is a float damping factor that is a constant typical of the PageRank algorithm. Okay, so we can receive messages from the other nodes if we aren't in the first superstep. So if we check if get superstep is greater or equal than 1, and if it's true, we sum all the values of the incoming messages. So sum equals to 0 initially, then for double writable message in list of messages, we increment the sum with the value of the message. In a second moment, we set the value of the page rank of the current vertex. So vertex value equals to new double writable damping factor 1 minus damping factor, and it is the page rank formula, divided by the total number of vertices. Plus the damping factor times the sum. And then we set the page rank to this value. Great. Now we check if we are in the last superstep. So if get superstep is less than max supersteps, we get our out degree, so long edges equals to vertex dot get num edges, and we send a message to all the edges, so all the other nodes. The first parameter is the ID of the current vertex, and the second parameter is the value of the message. That is, again, our page rank divided by the out degree. Okay. Instead, if we are in the last superstep, we vote to halt. Okay, let's see now the input file. This is for simplicity, a graph with only 5 nodes. The two main nodes are 1 and 3. They are the most probably relevant nodes in the graph. 1 and 3. They have 3 incoming edges. So let's see if, even according to the page rank, they are the most relevant nodes. We copy the input file in the Hadoop file system. Then we compile our class. And finally, we run. Okay. The output file. And we can see that the two highest page ranks belongs to the nodes 1 and 3.
That's all for today. We remind you that you can find all the material you're using in this tutorial at the following GitHub repo. Please contact us for any question or problem, and thank you for your attention.